SPH4U fields, 4.5 motion of particles in electric fields. So the milk and oil drop experiment was conducted by Robert A. Milken, who assumed that when oil droplets became a fine mist via a mist fire, they became positively electrically charged by the friction of that mist fire. So some of these droplets thus became suspended between two plates in a uniform electric field, and Milken could observe them with a microscope. So he then analyzed what happened to these charged particles in that uniform electric field by his microscope and mathematics. So right now we're going to go over the mathematics of this experiment, and we're going to find out theoretically what happened in this experiment. So two parallel plates are put 5 centimeters apart, and a drop is introduced with a mass of 1 times 10 to the negative 13 kilograms. And the potential difference of the plates is 120 volts. So this is a droplet that became suspended. So what is the sign of the charge on top? So if we go back in the call, the rules around electric field lines, we know that they go from positively charged objects to negatively charged objects. So since we know that it's going from the bottom to the top, we know that the top plate is actually the negative plate, while the bottom plate is actually the positive plate. So now we have the question, what is the magnitude of the charge on the drop? So first, let's just annotate this drawing. So we know that this is a negatively charged plate, so we have the force of electricity here because the positively charged particle is attracted to the negative plate, and since it's suspended, there's also force of gravity counteracting it and keeping it in equilibrium. So we know that it's in equilibrium, so they're actually equal. So Fe is equal to Fg. We can rewrite Fe via some of the equations that we know. So recall that we know that force equal to K Q1 Q2 over R squared, and E, so field strength, that's equal to K Q1 over R squared, and the V is equal to K Q over R. So we can rewrite this as Q over Q times E, epsilon, that's equal to mg. So the epsilon is actually equal to voltage over R, because epsilon is equal to kq1 over r squared, while voltage is kq1 over r. So if voltage is put over r again, then it will be equal to epsilon. So we can simplify this to v over r, so that's equal to mg. So now we just isolate for the q, so q turns out to be mgr over v. So that's equal to 1 times 10 to the negative 13 times 9.8 times 0.05. That is the difference between the two. So that's like the distance between the two plates, and all of that is over 120. So that comes out to be 4.1 times 10 to the negative 16 coulombs. So indeed, this droplet is positively charged. So from the last slide, we could see that this drop, it was kept in equilibrium via the electric force pushing it upwards and the force of gravity pushing it downwards. However, that's not always the case. Quite a few of those droplets actually got attracted to the negative plate because as one of the laws of electric charges states, opposite charges attract. So all the positively charged particles, they got attracted to that negatively charged plate. So yeah, and now we're going to move on to the final part of this exploration of the Milken experiment. So does the drop have an excess or deficit of electrons, and by how much? So in order to answer this, we would use this equation, Q is equal to NE. We're finding out how much, so we're looking for N. So N is equal to Q over E. So N is equal to 4.1 times 10 to the negative 16 all over 1.6 times 10 to the negative 19. So this comes out to be 2.5 times 10 to the power of 3. So since this is a positively charged droplet, we know that it's actually a deficit. Because when there's a deficit of electrons, something becomes positively charged, while when there's an excess of electrons, something becomes negatively charged. So deficit is equal to positive charge things, while an excess is equal to a negatively charged object. So that was the Milken experiment explained and explored.